So does anybody have any questions from page 33, questions 1 through 8 you'd like me to go over? Carly?
Number 5.
Okay, let's take a look at number 5. This one?
Yeah.
Okay. So white light contains wavelengths from 400 nanometers to 700 nanometers. This is something we know already. We direct that white light on a diffraction grating ruled with a certain number of lines per meter. The thing that we learned yesterday is that D, which is necessary to do any calculations with this stuff, is found by taking the reciprocal of that number, and that will end up giving us a value in meters, and I'm not going to worry exactly about what that is yet. Let's get to the physics of this question, not the math. What we have is a beam of white light, and this is why I have a dark background here, that's incident on a diffraction grating. And it doesn't matter what color I send through a diffraction grating, I will get a bright spot of that color directly across, and it's on the cross beam up there. So if green light goes through, I get a green dot there. If violet light goes through, I don't know if you can see it, it's very dim, violet light lands there. If red light goes through, red light lands there. So what that means is that when I shine that light through the diffraction grating, that light is white, I will get a white dot on the screen over here. So over here on the screen, I'm going to get a white dot of light. And I'm assuming that I have a nice narrow beam of light. But inside of that white light are all these different wavelengths. And the largest wavelength is the one that's going to be affected the most. We can either memorize that, because during refraction with a prism, the red light is not affected as much, and the opposite is true here. So what that means is that inside of this white light, the red light will end up landing over here. And by the way, there's going to be another beam of red light that lands down here. But at the other end of the spectrum, we have the 400 nanometers, which is a violet-y color of light. And it is not going to be affected as much, so it is going to be approximately like that. Now, unfortunately, I can't draw this realistically, but what will happen is you will get a rainbow of colors going from the Roy G. Biv in that order in this band that I'm indicating here that gets wider and wider and wider. So what you're going to see over here will be a, well, I'll call it a rainbow. It's not a rainbow. A rainbow appears in the sky, but I think you get my drift here. You'll see what we call a continuous spectrum of light showing all of the colors. And what this question is asking is, how wide is that spectrum? Because this is, I'm just going to use an arrow to indicate this. This is the n equals 1 for red. This is the n equals 1 for violet, which means that, you know, there's going to be another rainbow up there. There's going to be the spectrum of colors and the spectrum of colors above and below that white spot, and then out further will be the n equals 2 spectrum. So what we need to do here is determine this x value for red, this x value for red, and we also need to determine the x value for violet, and then we can subtract them, and that will be the width of the rainbow. Okay. We're probably going to have to do a well, technically we should do a calculation with lambda equals d sine theta over 1 to find out if the angle is less than 10 degrees, and then we can go ahead and use the x formula. So what is my D? My D is the reciprocal of 5.5 times 10 to the 4. That was in lines per meter, so it's 1.8, 18, etc. times 10 to the negative 5 meters. I'm going to go with the red wavelength in my calculation of theta because that would be the bigger of the two angles. I need to take that red wavelength, which is 7 times 10 to the negative 7, that's 700 nanometers. I need to multiply by 1 and divide by my D value and then take inverse sine. It's definitely less than 10 degrees. Okay. So now what you're going to do is you're going to use XD over NL to find equals lambda to find X for red, and then you're going to use XD over NL equals lambda to find out X for violet, and then subtract them. Yeah. Other questions? Okay. We're doing a lab today. I'm calling it a lab exam because I'm not going to be giving you much direction in terms of you're welcome. In terms of how you're going to get a solution to this problem, but I think you already have all of the tools necessary to figure that out. So let me hand this out first, then I'll just briefly, very briefly walk you through what you're going to be doing here in the lab to find the solution to the problem. I'm going to say that this is due on Monday. And once you see the scope of everything that needs to be done today, I think you'll agree that's fair. You could probably get it done for tomorrow. Did everybody get one? Did I miss anyone? Okay. So this says Physics 30 lab exam. It says you're going to be determining the specifications of a diffraction grating. And you can report your results either in lines per meter or lines per centimeter. It doesn't matter to me. Since you're going to be doing all of your calculations in meters, maybe just recording your answer in lines per meter is probably the best way to go about it. You're going to be measuring things most likely in centimeters, because the distances you're going to be talking about are less than a meter. But you can do those conversions. You need to work with a partner. There's an even number of people in the room, so you're working with one other person. You're not working on your own, and you're not working in groups of 3 or more. Materials you are going to be using there are 3 lasers, okay? So there are red lasers, violet lasers, and green laser pointers. The wavelengths are given on the lasers. If you have really good eyes, you can read it. It's such tiny print, but your eyes are young, you still have good vision. But I've put them up here for you, and they're on your handout as well. Please only take one laser at a time. You're going to be collecting data to find an answer to your problem using a red laser, and then you're going to be doing it with the other lasers as well. But I don't have enough laser pointers that if you came up and each pair of people grabbed one of each, we would run out. Okay, so grab whatever's available, collect your data, then bring it back and pick a different color laser. You're going to be getting a diffraction grating of unknown specification. I know what it is, but you don't. And one thing I neglected to indicate here, if you turn the page, on the bottom of the next page, there's a data table that you're going to be recording things in. I really should have put there something like diffraction grating, because all of the diffraction gratings have a letter on them. So this is N, this is H. And you need to record somewhere the letter of the diffraction grating that you have, because part of your mark is going to be based on how close to what I know the actual specifications are that you get. Does that make sense? So you need to record the letter of your diffraction grating somewhere. You use a meter stick. I also have rulers. You might need rulers for certain things. Paper, pencil, tape, anything else that you might find useful. And essentially what's going on here, I'll go with a green laser pointer for a demonstration, is you're going to take your diffraction grating, and I'm showing you this on the ceiling. You're going to be using the wall or the backsplash of a countertop. But essentially what it's going to involve is you measuring L, which is the distance from the diffraction grating to the ceiling here, except you're not going to use the ceiling. And you're going to have to measure X from that central dot to the n equals 1 dot on each side. Okay? So you're going to have an X on this side and an X on that side for n equals 1. Some students will think that the best approach here then is to take a ruler and measure that X on the left side, on your left side, write it down, and then do the X on the right side and write it down, and then average them. And that's okay. That's fine. The reason why you want to do that, by the way, and I'm going to really exaggerate things here, the reason why you want to look at both sides is because if your diffraction grating is angled, you see where those n equals 1 dots are? Well, if I angle my diffraction grating, those two distances, although I'm having a hard time here, those two distances, although they should be equal, are not, correct? Now, you're obviously going to be looking at your diffraction grating, and you will know if it looks like that. But if it's off even a bit, you want to average them to take that into account. There's a problem, and this is a Physics 30 thing that you could be asked about on exams. They're starting to ask more about scientific skills in terms of measurement. There's a problem with measuring on the left and the right and then averaging, and that's that you're going to have two sources of error. You're going to have an error in your measurement on the left, and you're going to have an error in your measurement on the right. So instead, the wiser thing to do is to measure the distance between the n equals 1 dots, and then just divide by 2. Why measure two things and add them together when you can just measure the whole thing? And that's why in your data table, if you take a look at your data table, it says red laser, and it gives you the wavelength. It says distance between the n equals 1 antinodes, and there's a blank for you to write the centimeters. By the way, it should be to the nearest tenth of a centimeter. Okay. Should actually be to the nearest hundredth, if you want to be technical. Because you can see on a ruler, let me show this to you. And again, this is something that you could be asked on an exam. You can see on a ruler, you can see where 5.1 centimeters is. There's a line there. And you can see where 5.2 centimeters is. There's a line there. Your job as somebody doing measurements is to be able to indicate where something lies in between those 2 points. Now, I know that you can, argue in this case that your dot that you're going to be looking at is probably wider than a millimeter, but you're trying to measure to the center of the dot. And I guess maybe to illustrate this idea, and I don't know that if we've talked about this before or not, but when you make measurements, you always record a value to one more decimal place than you can read. So if I'm asking you to measure where this box ends, well, if I'm asking you to measure where that box ends, I'm not going to do that. You know that it's someplace between 5.0 and 5.1. Is it exactly halfway? Because if it is exactly halfway, then you would record 5.05. I would say it's at 5.04 or 5.03. Do you get my idea here? I don't want to see any measurements recorded that are just so many centimeters. You should be looking at 2 decimal places, really, for the distances in centimeters. because you can read to one decimal place, you record to one more. Okay, so going back to the handout, if you take a look at it, you're going to measure the distance using, say, the red laser between the n equals 1 and the n equals 1 and record it. What are you going to have to do with that to determine your x that you will use in your calculations? Divide by 2. Now, you're going to be doing this, I mentioned this yesterday, you're going to be doing this along the side countertop. So I'm going to go to the far side of the room, even though it's furthest away from most of you, so that you can get an idea of what I'm talking about. You're going to have a ruler against the wall. You can hold it there or get a ruler that will stand on its own. It doesn't matter, but you can then put your diffraction grating against the edge of the countertop. Okay, it's just sitting like this, just on the edge of the countertop, and that way I can measure L. Now, my advice to you would be when you shine your laser through the diffraction grating, don't shine it on the ruler, shine it above the ruler that's against the wall. Because if you shine it above the ruler, then the backsplash of this countertop, that's what this is called, is the screen. So L is simply the distance from the screen to the edge of the countertop. You can measure that. That's L. So you're going to know L. You're going to know X for that data point by taking your distance measured and dividing by 2. You're going to know N because it's N equals 1. And you know the wavelength because it's given to you. You should be able to find the value of D, which will lead you to the specifications of the diffraction grating. Are you still with me? Okay. The question I have for you, and I'm not going to answer it, I think it's quite obvious, but you're going to have to think about it maybe, is which formula are you going to use here? Well, we've done enough of these that you know you have to determine the angle, and if the angle is more than 10 degrees, you know you can't use the lousy formula. Well, I think you'll be able to, quite frankly, look at this and make a judgment of what you think the angles are. But that's not good enough in a lab report. You need to show a calculation of an angle to indicate why you're using the formula you're using. Are you with me on that? Okay. So then you're going to do that for the n equals 1 for red. You're going to collect data for the n equals 2 for red. You're going to do the n equals 1 and the n equals 2 for green, the n equals 1 and the n equals 2 for violet. You're not going to collect one set of data and then do the calculations. Collect another set and do the calculations. You're going to collect all your data. Now, under the analysis here, which would be on the next page, I only want you to do a complete set of calculations for, I think I said the n equals 2 for green, for the n equals 2 for green. So when you summarize your report somewhere, you can just put that I found the specifications to be this number for n equals 1 for red, this number for n equals 2 for red, this number for n equals 1 for green, et cetera, et cetera, et cetera. But in the analysis, I just want to see one complete set of calculations. You don't need to show me how you got those specifications for other data points. Then your final analysis should be to take all of your D's and average them, or all of your specifications and average them. So you can find specifications for each one and then average those. Or you can find D's and average those and then find the specifications. But you do not want to do anything crazy like averaging your X's or averaging your... It doesn't work that way. All right? Do you get the idea of what it is you're after here? I also want you to do an evaluation. Normally an evaluation involves a % error, but you do not know what your particular specifications are. So your evaluation will be based on looking at all of your specifications and seeing how close they are to the average. You know, you're going to get an average, and let's just say that your average is bang on. But if you've got numbers that are 30% on one side of the average and 30% on the other, that's not a good lab. You need to improve something. And by the way, I'm asking for a procedure here. I'm asking for the experimental design. which would include a picture, a diagram showing what's going on, and a description of how you would collect your data. My idea for the expectation for a procedure at this level is if somebody's not here today and they came in tomorrow and said, I want to do the lab, I should be able to take your procedure and give them the materials and they would know exactly what to do. It's a recipe for how to complete the lab report. So I'm expecting a level of quality here. You know, can you do all of the work and get a good answer and not get 10 out of 10? Absolutely. It needs to be organized, it needs to be neat, it needs to be well constructed. I'm looking for a level that's appropriate to a grade 12 physics lab, not a grade 9 science class. So groups of 2, lasers are all up here. If you have difficulties with the lasers, it could be that the batteries are dying. So, you know, don't turn your laser on and hold it there for 20 minutes. You're just going to drain the battery. I might recommend using sheets of paper on the backsplash and putting it there, trying to hold it really steady. And then you can put marks on the paper, and then you can do your measurements later. I think I have some masking tape. You can put masking tape there. But if you're going to use masking tape, don't put it on there and take your put marks and then peel the tape off and measure. Because when you peel the tape off, it changes length, stretches. There's rulers up here. There's additional meter sticks. I think you're good to go. So let's get started. I'm not going to dim the lights. The violet light is really difficult to see.